In previous lecture, we started chapter number 12, current electricity, and now we will continue this chapter. We will discuss resistivity or specific resistance, conductance, conductivity, effect of temperature on resistance, temperature coefficient of resistance, variation of resistivity with temperature. Let's recall electrical resistance. We have already discussed electrical resistance and factors that affect electrical resistance in previous lecture, and the important points discussed are: resistance is a measurement of how strongly an object will oppose current. An object's resistance depends on four factors: resistivity, length, cross-sectional area, and temperature. Resistivity is specific to a material. The higher it is, the more natural resistance the material has. Today we will discuss resistivity in detail. Resistance depends on length. How long is the object? The longer it is, the more it will oppose current flow. Resistance also depends on cross-sectional area. How big is the object across? The wider it is, the more current it will allow to pass. Electrical resistance also depends on temperature. If the object is warm, the molecules inside will be bouncing around more, opposing current. So, in conductors and metals, with increase in temperature, resistance increases. We also derived this relation R is equals to rho L upon A in previous lecture. R is resistance, rho is resistivity, L is length, A is area. Unit of resistance is ohm. We would like to have conductors that allow current to flow from one place to another easily. Ideal conductors have minimum resistance. How should be an ideal conductor? Hot or cold? Wide or narrow? Long or short? Answer is the ideal conductor has a low resistivity and it is short, wide and cold. Cold means low temperature. Shorter conductors have lower resistance because electrons do not have to travel as far. Wider conductors have lower resistance because electrons have more room to pass. Colder conductors have lower resistance because atoms are not as energetic, don't interfere with electrons at low temperature. Factors that affect resistance, we have already discussed this in previous lecture, but I'm just recalling it. As we know that resistance is equals to rho into L divided by A. So with increase in length, resistance increases. With increase in area, resistance decreases. And with increase in temperature, resistance increases in conductors. Now coming towards our today's topic, resistivity. Resistivity is inherent property of a material. The resistance of a wire is directly proportional to its length and inversely proportional to its cross-sectional area. R is equals to rho L upon A. So by rearranging this formula, we can have resistivity rho is equals to R into A divided by L. The constant rho, the resistivity, is characteristic of the material. It is inherent property of the material. If a wire is having cross-sectional area of 1 meter square and length of 1 meter, then by putting A is equals to 1, meter square and L is equals to 1 meter. In the formula rho is equals to R into A divided by L, we will get rho is equals to R. That is the resistance offered by 1 meter length of wire of a material having an area of cross section of 1 meter square is a specific resistance of the material. The unit of specific resistance or resistivity is ohm meter. Resistivity depends upon the nature of the material and temperature of the material. Resistivity is independent of the dimensions of the conductor. The resistivity of metals and alloys is very small. That's why metals are good conductor of electricity. The resistivity of insulators is extremely large. That's why they do not conduct electricity. The resistivity of semiconductor substances lies between conductors and insulators. Conductance. The conductance represented by capital G of the conductor is the reciprocal of its resistance. Mathematically, G is equals to 1 upon R. G is conductance and R is resistance. It shows that with increase in resistance, conductance decreases, and with decrease in resistance, conductance increases. In simple wording, high resistance means there is opposition to flow of current, so conductance will be decreased. Minimum resistance means opposition to flow of current is reduced and current can easily flow, hence conductance increases. Unit of conductance is mho, ohm spelled backward, or Siemens. Conductivity. The conductivity represented by sigma of a material is the reciprocal of its resistivity. Mathematically, conductivity sigma is equals to 1 upon rho resistivity. This shows that with increase in resistivity, conductivity decreases, and with decrease in resistivity, conductivity increases. Unit of conductivity is mho per meter or Siemens per meter. Effect of temperature on resistance. We have already discussed these points in previous slides. The resistance of metal increases with the increase of temperature. When we increase the temperature of metal, its resistance also increases. The resistance of insulators and semiconductors decreases with the increase of temperature. When we increase the temperature of insulators or semiconductors, their resistance decreases. Temperature coefficient of resistance. Now we will derive temperature coefficient of resistance. Consider a conductor having resistance R0 at 0 degree Celsius and RT at T degree Celsius. Here R0 is initial resistance of the conductor at 0 degree Celsius and RT is final resistance of the conductor at T degree Celsius. T degree Celsius is final temperature of the conductor. It has been found that the increase in resistance RT minus R0 is directly proportional to initial resistance R0 and directly proportional to rise in temperature. So RT minus R0 change in resistance is directly proportional to R0 initial resistance of the conductor and RT minus R0 change in resistance is directly proportional to T the rise in temperature. By combining equation 1 and equation 2 we get RT minus R0 is directly proportional to R0 T. Here constant of proportionality is alpha and we get RT minus R0 is equals to alpha R0 T. Alpha is temperature coefficient of resistance. RT is equals to R naught into 1 plus alpha T. Solving for alpha, we get alpha is equals to RT minus R naught divided by R naught T. From this relation, we can define temperature coefficient of resistance as increase in resistance per ohm original resistance per degree rise in temperature. Or in other wordings, we can say that the fractional change in resistance of a substance per Kelvin is called temperature coefficient of resistance. Its unit is Kelvin inverse. Variation of resistivity with temperature. The fractional change in resistivity of a material per Kelvin is called temperature coefficient of resistivity. The resistivity of most material increase linearly with increase in temperature. We know that alpha is equals to RT minus R naught divided by R naught T. As R is equals to rho L upon A, we can put RT is equals to rho T L upon A and R naught is equals to rho naught L upon A in above equation, and by solving we get alpha is equals to rho T minus rho naught divided by rho naught into T. By rearranging and solving, we get rho T is equals to rho naught into 1 plus alpha into T minus T naught. SI unit of temperature coefficient of resistivity is Kelvin inverse.